You might just find yourself exploring out in great Mother Nature, and you discover a core shot that is supposed to sustain you or a loved one. And you might ask yourself, when do I tie the knot? Not for the loved one, but for the rope itself. This is the question we want to answer, because the Alpine butterfly comes into the scene, but maybe the damage of that rope is less effect on the strength than tying the knot itself. Where is the threshold? So are you going to tie that knot or not?
My name is Tyler.
My name is Paul, and this is our 8-foot specimen, ready to be tied for the Alpine butterfly pre-damage to understand what our load rating is, or rather our effect on our rated load, and that's where we're at. But we need to connect this sensor and making sure that the load frame is actually giving us our data. Hello there. You might be asking yourself, what kind of strength does my rope have by itself? And also, what kind of strength does this rope have when I tie a knot in it? Specifically, the Alpine butterfly. There is a loss in strength when we tie a knot into our ropes. And further, if we damage the rope, say by getting a core shot, which means that the outer sheath is broken, there is an even further reduction in strength. We wanted to know exactly what that threshold was when you compare a rope by itself and then when you tie the knot in it, and how that compares to the amount of damage that you might have in a rope. Because the whole idea with the Alpine butterfly is that it can isolate damaged sections of rope that we might be using. So there might be a time when it actually makes sense to just leave that core shot by itself and not tying the knot. What we're doing here is exposing the core strands. So we have a little razor blade here, and I'm just taking an incision or mid-span, trying to be careful to not cut into those core strands. It appears our knife is dull. But what we're doing here is just slicing that, and then once we expose a little bit of that orange, we'll then be able to grab one of the core strands and then make a cut. And so that's kind of what we're doing. So we're gonna do 2 bundles, 4 bundles, and 6 bundles cut to see what kind of failure difference we get in the behavior between these 3 compared to our control.
This was our no damage Alpine butterfly rope strength test. We observed it broke at the knot. However, this one didn't break until 12 kilonewtons this time.
All right, so we're running our 3rd Alpine butterfly test.
It's creaking a lot. Did I? Wait, hold on for that. Okay, we found in test subject 1 with 1 bundle cut that it did not fail at the cut location. Instead, it failed near the knot.
Okay, here we have 2 bundles cut from our core, and we're gonna see what we get with this result.
Now with 2 cuts, it breaks at the cut this time, and it whipped all of the strands out from this side, which are now hanging here. This is our 6 cores cut, and on this one, it broke at the cuts on the cores around 9.43 kilonewtons. Today we are testing a static rope. So we are doing a control, which is just an Alpine butterfly tied off to 2 figure 8s on each end of the rope. First one failed at 12.54.
This is test 3 of the Alpine butterfly midline assessment, just to see what kind of reduction in strength we get from tying the knot.
Right now it's around 12.2 to 12.5 kilonewtons.
Okay, we are now testing the midline without any knots tied in it so that we get a baseline of what the strand strength is before any reduction via knots or damage.
We're seeing that without the Alpine butterfly, apparently the rope is weaker. The max force was 12.15. This does not make sense. Therefore, we're going to do more tests to get better data.
This is our sample set of our non-dynamic, aka static rope with bundles cut. This 4-strand composition is much more fine than the braided dynamic rope that we were working with previously. So it was kind of challenging to get an exact cut of 2, 4, and 6 bundles. That's still out of 12 core strands that we were able to identify with this one. But you can kind of see, here is our 6 bundles cut. And that one has a lot more cut out of it, of course. Then this is our 2 bundle and our 4 bundle. So definitely can see a little bit of a difference in how much was cut with each one, but now we're going to test it on the load frame.
We started with 2 types of rope, static and dynamic. From there, we cut each rope into equal length specimens. On those specimens, we tied a figure 8 on a bight on each end. This allowed us to connect the specimens into the load frame used for pulling these specimens apart. From there, we tested a control for each, which is just no knot in the middle, no cuts, just the strength of the rope alone. After that, we did the strength of the knot in the rope. So you have your figure 8s, and then you have the Alpine butterfly in the middle. And then we moved on to our percent depth cut.
We wanted to figure out exactly how much we were damaging the rope. So we dissected the thing, and we found that it's made up of a sheath and bundles. And these bundles in the core of the rope are woven together. There was 12 bundles total for each rope series that we did. So we cut 2 out of 12, then 4 out of 12, then 6 out of 12. That gets us from 16% of the core strands cut all the way up to 50%, which would be a significant core shot. Okay, so this is the interesting thing. When we tested the static rope, we saw that there wasn't as much reduction in strength as we initially thought there might be. We did see as a general trend that strength in the rope did taper off as we got to 6 bundles cut. It really did start to decrease. However, we could keep in mind that even with the 6 bundles cut, we are getting values over 8.5 kilonewtons. And for your reference, a typical climbing fall on a dynamic rope, it might be anywhere from 5 to 9 kilonewtons.
Then, looking at the dynamic rope, when you look at the control to the Alpine, you see a noticeable decrease in the strength. However, as you continue down the amount of bundles cut, going from 2 to 4, you notice that the strength is still slightly above the knot value. But when you go from 4 to 6, you notice a large decrease in strength.
But of course, the study wouldn't be complete if we didn't talk about our limitations. So let's get into it.
Most notably, we only had a limited amount of rope to work with. This led to us only being able to do 3 tests per group. To refine this experiment in the future, we would have loved to do 10 or 15 per group to see how our results would be refined.
So thankfully, we have testing capabilities given that we have access to Montana Gear Lab. But the limitation with this machine is that it's a quasi-static scenario, which means that a winch is pulling on the rope continuously. And that's just not very accurate for a real-world scenario where you might have somebody climbing and they fall and they have a much more dynamic loading experience on that rope itself. We get pretty far with the resources that we have, and it's super great just to be able to see what we can see. But we'd be really interested what kind of outcomes we would get if we had this dynamic loading scenario to be able to test.
Like that?
I think so.
I think that was okay.
Yeah.
I'm thinking like jazz hands, baby.
My name is Paul, the other half of the Dongling Butterflies.
Hi, it's my shot. I'm here providing moral support to Tyler and Paul. They're doing a great job.
Those scissors, it seems like you're kind of providing some other kind of motivation. Jacob is watching Instagram Reels right now. So the background audio may be affected, but regardless, we will persist. like this rope is persistent. Jacob! 4 bundles. Let's see how it goes. Okay, I just ate an orange, and so you can see some of the residuals on that, so don't pay any attention. It's not eczema.
We're doing another to be statistically correct. Engineers.
What does statistically correct even mean?
It sounds cool. No, I would say to be statistical, because like we based everything off of the 9 kilonewtons. But then to be statistically correct, you have to base it off of.
What is statistically correct? Do you mean significant, or do you mean you just have error bars?
So you might be asking yourself, I don't know if we should do that.
To see how our results would be defined.
Refined.
Fine. That was good.